Welcome to Academia. Today we shall study gradient of a scalar field. Now what is a scalar field? Suppose a contour has surrounded a region called R, and this region R contains infinite number of points within it. Suppose P is an arbitrary point within this region R. Now since the region R itself is two-dimensional, a two-dimensional Cartesian coordinate system is enough to specify the position of the point P. Say the coordinate of P is xy, which indicates its position within the region R. Both x and y are scalar variables. That means position of any point in this region R can be uniquely determined by the coordinate xy with different values of x and y. Say f is an operator or a function which is defined over this region R. So for every point xy, fxy will be defined. Fxy produces different scalar values for different points within the region R. Hence, f can be called scalar point function which forms a scalar field over the region R. Suppose we have a region of points where fxy is constant for each and every point. Say fxy is equal to c, where c is some arbitrary constant. Now, if it is a two-dimensional region of points, then it will produce a contour. If it is a three-dimensional region of points, it will produce a level surface. So, if xyz equals to c will produce level surface. Say fxy is equal to x square plus y square. Then x square plus y square equals to c equals to k square, where k is some other arbitrary constant. Then it is equation of circle. Hence a circle is a contour. For three-dimensional region of points, say if xyz is equal to x square plus y square plus z square equals to c equals to k square. Then it is the equation of a sphere, that is spherical surface. So this is a level surface and this is a contour, and the value of the function f at any point on this level surface is constant, that is the value c. Whereas on every point on this contour, the value of the function f is constant, which is c again. We shall work with this three-dimensional spherical surface. Let me draw the sphere as a circle on this two-dimensional plane of whiteboard for both of our convenience. Say S1 is a spherical level surface and the value of a scalar point function f is constant over the total surface of S1. Say that constant is c. So if xyz is equal to c. It is not fxy, I have made a mistake here. It will be fxyz instead. So if xyz is equal to C for S1. If C has a different value, then f xyz will produce a different surface. Say for our convenience, we define this function f xyz as v of xyz. Again a mistake, it is not vxy, it is vxyz. Say vxyz is equal to v1, that is a constant value, produces this surface S1. Then for vxyz equals to v2, a different constant value, we shall get a different level surface S2. Say P is an arbitrary point on the surface S1. The position of P can be uniquely determined by this 3D Cartesian coordinate system whose origin coincides with the center of the spherical surface. So both S1 and S2 will be concentric spheres. Let us join the origin and the point P and extend the line until it cuts the outer spherical surface at a point Q. So value of the function at P will be v1 and value of the function at Q will be v2. The interesting thing is, at any point on this outer spherical surface, the function has the same value, v2. So, at any arbitrary point R on the surface S2, the function will have the same value, v2. So, Vr is equal to v2. Let us join P and R. Now the value of the function changes from v1 to v2 between the points P and Q. Similarly, between the points P and R, this change of the function is same, that is v1 to v2. Now, if we want to know the rate of change of the function f, which is v here, from the surface S1 to S2, how do we find this rate of change? The measure that we use to find this rate of change is actually gradient. We know gradient means slope, and slope signifies rate of change. Say the surfaces S1 and S2 are very close to each other, then the change from v1 to v2 is very small, say dv. So v2 can be written as v2 is equal to v1 plus dv. Say we want to measure the rate of change of the function v from both p to q and p to r. We know the distance between p and q is not same as the distance between p and r. So pq is actually not equal to pr. Say pq is equal to dn and pr is equal to dl. Now r is an arbitrary point on S2, whereas both p and q are on radius. So pq is in the radial direction, but pr is not in the radial direction. Now, to measure the rate of change of v in pr direction, we shall use change in the function by PR. So change in the function can be written as del V. So del V by PR is equal to dV dl, since PR is dl. Now if we want to measure the rate of change of V in the PQ direction, that is in the radial direction, then we shall use del V by PQ equals to dV dn, since PQ is dn. Now this is the rate of change of function in radial direction, whereas this is the rate of change of function in any arbitrary direction. Say the angle between these two different directions is theta. We know radius intersects the spherical surface at 90 degree. So PQ will be perpendicular to QR. Then PQ is base, PR is hypotenuse. We know base by hypotenuse is equal to cos theta. So PQ by PR is equal to cos theta. Now PQ is dn, PR is dl. So dn by dl is equal to cos theta. Then dl is equal to dn by cos theta. So we can write the dv dl is equal to dv dn into cos theta. So rate of change of the function v along PR direction is dv dn cos theta. Now if theta is 0 degree, cos theta will be maximum, that is 1. Then dv dl will have the maximum possible value. So the rate of change of v along a direction where theta is equal to 0 degree will give us the maximum rate of change. So maximum dv dl will be dv dn. And dv dn is the rate of change of v in the PQ direction. That is, maximum rate of change of v occurs in the direction PQ, which is radial direction. So maximum rate of change of v occurs in radial direction. This maximum rate of change of v is called gradient. That is, maximum dv dl is equal to gradient of v, and gradient of v is denoted by del v or nabla v. Del or nabla. So maximum rate of change occurs in radial direction only, not in any other arbitrary direction. So gradient of v has got a particular direction associated with it. Hence gradient of v is not a scalar, it is a vector. That is why we put a vector sign over gradient of v. Now, how do we describe gradient of v in three-dimensional Cartesian coordinate space? What is the change in function from v1 to v2? It was dv. Now we already know that dv dl is equal to dv dn cos theta. And dv dn is equal to gradient of v, which is a vector. Hence, instead of writing dv dn cos theta, we can write it as grad V dot 1L, where 1L is a unit vector along the direction of dl, that is P to R. So magnitude of 1L is 1. So if we find dot product between grad V and 1L, we will get dV dn, and cosine of the angle between them. Now the direction of 1L is along PR and the direction of grad V is along PQ, and we know the angle between them is, say, theta. So it is dV dn cos theta equals to grad V into 1L vector. So dV is equal to grad V into dl 1L vector. dl is the magnitude, 1L is the direction, that is the unit vector along dl. So dl 1L can be written as dl vector. dl vector is actually in the direction from P to R. This is dl, this is dn. Say P has coordinate x, y, z. So to go from P to R, there will be changes in x and in y and also in z. Say the changes are dx, dy and dz. Then dl will be dxi plus dyj plus dzk. Now dv can also be written as del v del x into dx plus del v del y into dy plus del v del z into dz. This is a very well-known partial differentiation form. Now these two expressions of dv are equal to each other. How do we equate them? It's very simple actually. Grad v can be written as del v del xi plus del v del yj plus del v del zk dot dxi plus dyj plus dzk. Now see, the result of this dot product evidently matches this expression. Then grad v can be written like this. Let's write it once again. So grad v is equal to del v del xi plus del v del yj plus del v del zk. We can bring v out of this expression like equals to del del xi plus del del yj plus del del zk v. So grad v can be written like this. Then what is this del operator or nabla operator? Del operator is actually equal to del xi plus del yj plus del zk. So gradient itself is a vector operator which operates on a scalar to produce a vector. Now, what is the nature of this vector? We shall try to understand this with a simple known example. We know that E vector is equal to minus dV dl, where E is equal to electrostatic field, V is equal to electrostatic potential. Now say our function V is this electrostatic potential function. We know that the direction of E is always radial to the surface. If a charge is at the center within a spherical surface, then E will emanate through the surface radially. Then the direction of E will be along radius, in the radial direction. PQ, which is also the direction of grad V. dV dl is rate of change, grad V is also rate of change, so it can be easily written as minus grad V. So grad V produces a vector E, which is an electrostatic field, that is a vector field. So gradient of a scalar field produces a vector field. We shall discuss vector field in detail in the class Divergence of a Vector Field. Thank you. Don't forget to leave your feedback in the comments below and tell us how do you like our classes. So if you wish to attend our offline classes, you are most welcome to visit our tutorial home at New Goria near Kavi Subhash metro station. So the students of West Bengal University of Technology, popularly known as WBUT, can subscribe to the YouTube channel of Pandora's Reel and can avail all the classes for free.